Hello. Today in this video, we're going to be talking about the limits of trigonometric functions without using L'Hopital's rule. So the first thing you guys need to know is these two limits. The limit as x approaches 0 of sine x over x equals 1, and the limit as x approaches 0 of 1 minus cosine x over x equals 0. So I won't be proving this limit in this video, however, I will be proving this one. It's just proving this one is a little bit more in depth, but so to evaluate this limit, the first thing that I'm going to do is multiply by the conjugate of the numerator. And this helps me because I can turn this into 1 minus cosine squared, difference of squares. Right? So we know that 1 minus cosine squared is actually equal to sine squared because of the identity. It's called the Pythagorean identity. Sine squared x plus cosine squared x equals 1. Therefore, sine squared x equals 1 minus cosine squared x. So this is the limit as x approaches 0 of sine squared x over x times 1 plus cosine x. And I'm going to split that into sine x over x times Now we know this limit is 1, as said earlier. So that's 1 times, plugging in 0, we get 0 over 2. And that's 0. So that limit we've proved to be 0, using the fact that the limit as x approaches 0 of sine x over x is 1. Okay, so using this information, let's try a few examples. So the first example is that the limit of x approaches 0 of tangent x over x. So remember that tangent x is sine x over cosine x. So I'm just rewriting that as sine x over cosine x. Then I'm rewriting this as sine x over x cosine x. Now I'm going to split up this limit by breaking apart this fraction into sine x over x times limit as x approaches 0 of 1 over cosine x. So we know that this equals 1. And by plugging in 0 here, we get 1 over 1, and all of that is equal to 1. Now, for this limit, you'll notice that it's similar to this one, but these two numbers just don't match up. So what I'm going to do, the trick here, is multiplying the entire fraction by 1/2 over 1/2. I can do this because that keeps the entire expression equivalent, because 1/2 over 1/2 is just 1, and multiplying a fraction by 1 keeps it equivalent. Now you'll notice that we have something that looks like this. I'm going to take out this 1/2, factor out this 1/2, and then I'm going to say this is sine 1/2 theta over 1/2 theta. And you could think about this as just setting x equal to 1/2 theta And as x approaches 0, 1/2 theta approaches 0 also, or you can just look at this and see that these two numbers are the same and it approaches 0. So this is 1/2 times this limit, which is 1, and that equals 1/2. Now for the next example, we're going to do something similar. Actually, the trick here is first I'm going to multiply by x over x. Then I'm going to rewrite this like this. And then I'm going to multiply the fraction on the top and the fraction on the bottom by something. I'm going to multiply the fraction on the top by 3 over 3. Then I'm going to multiply the fraction on the bottom by 5 over 5. Notice that I'm trying to get the argument of sign to be the same as the denominator so that I can apply this limit. So anyways, that works out to limit as x approaches 0 of, take out that 3, sine 3x over 3x, and all of that, oh, I don't have space here, we'll go down here. These two limits are just one. Limit as x approaches 0 of this, and limit as x approaches 0 of this. So it's 3/5. So to approach this one, I'm going to use this limit. So when I'm trying to get this limit into this form, I'm going to do this. Notice how we've gotten like these limits into this form. So after that, what I'm going to do is split this fraction. And I guess that you could say that you can also split the entire limit itself too, definitely. Now you might be thinking, multiply both sides of this fraction by 3 and here by 4, and you're right. I'm going to multiply the numerator by 3 and the denominator by 3. And then on this side, the numerator by 4 and the denominator by 4. Then I can factor out this 3. I can even move it outside of the limit if I want to. Same with this 4. And this equals 0, and this equals 0. So it's 3 times 0 plus 4 times 0, and it's just 0. You're probably wondering why I did all this work just to get 0 and taking this out, and even when you know it's 0, well, it's just about proving that it's 0, and as with all of these trig limits where you have to use this property, you obviously get either 0 over 0 or, I don't think in any of these, but infinity over infinity. You get indeterminate forms, and that's why these limits help. And they're very useful until you, and also after, in conjunction, when you learn about L'Hopital's rule. So thanks so much for watching. I have a few more problems that I'd like to go over, and I'm probably going to make a part 2 for this video. But if you enjoyed this and found this helpful, I would really appreciate if you could like or subscribe. And if you have any questions about what I did in this video or any video suggestions, feel free to drop a comment. Thanks so much for watching.